The AI podcast brings you new and innovative insights from AI and machine learning researchers and developers. The podcast is brought to you by your co-hosts, Arjit Sirkar and Christian Hart. In today's episode, we will be talking with one of the authors of the recent paper, Neural Compression of Atmospheric States. Piotr and the team responded to the challenge that data scientists can't afford to store the vast amounts of data they need, and the team have produced a new compression method that is truly impressive. So, Arjit, as always, very excited. Piotr is an amazing guest for us to have. Really interesting guy. So I think this is going to be fun. What are you excited about?
It is. I'm excited because and we'll get into more details later on, right? But I'm really amazed by the potential of this paper because it's an enabler. It enables a lot more research to happen in this field, which is arguably one of the, I think the top level outcomes for AI if we can do this. I mean, if we create a human robot, great. But if we can solve weather, climate, I think that's next level.
Yeah. People talk about AI for good. This is right in the crosshairs of that. It's exciting to find a really good use case. But before we dive into it, as always, I want to give our audience the II fact of the day. We always like to remember our mascot. Today's II fact of the day is IIs are the world's largest nocturnal primates. They rarely descend from their treetop nests during the day, preferring to forage at night. Maybe they're just shy. Who knows? Arjit, would you like to introduce Piotr properly?
Sure. So today we have with us Piotr Mirowski. He's a senior staff research scientist working at DeepMind. He did his PhD at NYU under none other than Professor Yann LeCun. His interests are in weather modeling and forecasts. Obviously, that's where we are today. But he's also interested in human-computer interaction and the use of AI for artistic human and machine-based co-creation. So welcome, Piotr. We are really, really happy to have you.
Hello. Thank you so much, Arijit and Christian. I'm delighted. Yes, I'm very happy.
So yeah, before we jump into the paper in depth, maybe just a little sidebar on the human and AI or machine co-creation. That sounds fascinating. What's that about?
Yeah, it's a very good question. I think the word co-creation is very interesting because you are stating the fact that the machine can be used as a tool, but at the same time you're giving it some form of agency. And this is essentially what happens with AI systems currently. So I have been looking for the past few years from an academic point of view at human-computer interaction studies around how AI systems can be used for storytelling, as tools for writing, how they can be used as tools for illustration. And there is research I conducted at Google DeepMind on that subject specifically. I think a few months before ChatGPT was released, we had actually worked with 15 playwrights and screenwriters, having them assess a system we had developed called Dramatron that could be used to help co-write screenplays in some way. And we interrogated and expected very critical feedback from the screenwriters and playwrights about if there was any utility whatsoever and what were the many ethical concerns due to that tool. And we had some interesting observations about what would be the expectations of an industry professional working with that kind of tool. So they want to retain their own agency. They do not believe those kind of tools can create work on their own, but they can be sometimes useful for ideation. What I'm saying right now doesn't sound any surprising at all, simply because we've had so much discussion and exposure to those tools in the past 2 years. I followed up that work when I was at Edinburgh Fringe, talking to comedians, how they use generative AI and hearing their concerns about the lack of alignment between the way the language models are trained and how they can moderate a bit too much at the wrong time for the wrong reasons, the generation, or how they just generate things that sound like cruise ship comedy from the 1950s or 60s, slightly less racist, but still really, really bad, really bad. And as technology develops, of course, sometimes those tools get better, but it's very important to really understand how they can be leveraged in the way that empowers the artist and the creator and responds to all those ethical concerns.
Just thinking, comedy is one of the more complex forms of language we have, isn't it? I mean, so much is inferred, so much is contextual.
Yes.
It's not, I was saying to Arjit when we were planning this, it's not like tell me the way to the post office, which is just a pure simple statement. A joke is rarely easy to explain to someone. It's one of those things about do people from other countries understand British humour? It's been one of those ongoing jokes itself for many, many years. But I was just thinking that must be it in one way it sounds trivial, but as soon as you think about it, it's not trivial at all. It's actually an amazingly big challenge to work on. I love it.
And I was reacting like first of all, like two things, like comedy and humor. There's a lot of intelligence behind that, right? And we're talking about like AGI and stuff like that. That's why like comedy is termed as wit, because wit again is intelligence. So it's like an indicator of intelligence in societal circumstances. Humor certainly does that. And the second thing, what you touched upon, the regulation, moderation side of things, is humor is on the edge, is really on the edge and pushing those boundaries, right? And if you moderate too much, your humor falls flat. You don't want it to be racist. You don't want to be, like proper dad jokes. Somewhere in the middle is yeah. So it's very, very interesting.
Yes, I wanted to add that. So this interest of mine in human-computer interaction comes from a personal project I've been doing in parallel, quite seriously actually, because I've been doing improvisation and improvised comedy with robots for the past 8 years, with the language models, bringing them on stage. Don't ask me why I started this. It has to do with language models and theater training, where in both cases, we're trying to do the most obvious thing. Language models is all about modeling what comes next. And when you're on stage in front of the audience, you also just try to be as spontaneous as possible. It's a strange parallel. I found that parallel interesting, and so I decided to bring a robot on stage and a language model on stage. But the interesting aspect of improvisation specifically, as it relates to comedy or theater in general, is or jazz. It's how it has been defined as real-time dynamic problem solving by researchers in computational storytelling. So you have a system that is deployed real-time and that is resolving a problem all the time, constantly and adapting. So improvisation is, in a way, what you manage to reach once you know your subject very well. You've been trained enough, and when you are listening to all the elements of a context. So a jazz musician playing on the piano and listening to what the rest of the band is playing, and then using the muscle memory and other culture to play something that sounds well of the same on stage, when you are listening to the minute facial expressions and some references made at the beginning of a scene, and you respond to that, incorporate it. This is the sort of contextual intelligence that we're looking for in performance in performing arts. So now, how do you make that work? It's probably impossible, but that's the fun challenge with a group computer.
It's a great challenge. Love it.
Fascinating.
So you got your PhD in 2010. You've gone through Bell Labs, Microsoft, most of the rest of the time at DeepMind. You've been in the center of things through this kind of AI revolution. We all know that AI has been around since 1955 or something or other. And there was an interesting spike in the 70s as well, and then there was a kind of winter. But this latest blossoming, you've been right through it. For most people, the kind of AI started with ChatGPT, and they were kind of, oh yeah, that's a thing. Because everyone forgets about self-driving cars and all the stuff that we were doing then. But I just you've just got a really unique view on this. That I just what's it been like for you, going from the early 2000s through to now? How's it been on the inside?
I think it's good to have been in that field long enough to see the fragility of our systems. I still remember logistic regression and all those linear classifiers that are simply looking for elements in the input and building a decision, basically making the decision based on linear contributions of each of those elements. The reason why this is interesting is because it keeps you grounded on the fact that you need a good data to train those models to begin with. There has been an amazing change, of course, in the complexity of the hardware and in how you build and deploy your models. It's not quite reassuring not to be able to code everything from scratch by yourself. When I was doing my PhD, I could actually implement a neural network in MATLAB with backpropagation, starting from the basic fundamental equations. It's not something people do these days anymore, and as a consequence, we may sometimes lose a bit track of what actually is going in the system.
Yeah. So effectively, you would recommend to people coming into this field is like, yes, use the libraries because they're optimized and all that kind of stuff, but know what they're doing rather than just blindly just use the functions built into them.
I think I would recommend that, and it can be something as simple as just building a spam filter that is literally looking at the linear contribution of different words to the final output.
So before we get too much into the paper, now obviously we have let on that it's about climate, it's about weather. But do you want to tell us about the general problem space, right? Where are we operating? What are we trying to solve here?
Yes, so this work is part of a larger effort we've been doing for the past few years at Google DeepMind and also at Google Research, which is to look into modeling weather and climate and more generally looking at questions around sustainability, which may not necessarily involve modeling weather variables, but maybe also modeling the impacts on agriculture, for instance. So it started for me personally 19 when we started working with a Met Office on weather forecasting. And we were ingesting huge amounts of data provided by the Met Office in order to predict precipitation. So the amount of droplets in the atmosphere as measured by a Doppler radar at a very fine resolution of a kilometer in every 5 minutes and looking at data of many years. So we were manipulating huge data sets already, which are commensurate with the size of data sets you get when you train a more general image generator or a language model. So that work on weather forecasting or weather nowcasting got our team really starting in that field. We had a paper in Nature on nowcasting the next hour of rain using video GANs, generative adversarial networks, but generating videos and generating different outcomes. And then the team continued working on weather forecasting at the horizon of 2 weeks, predicting at a global scale this time and at multiple levels of altitude in the atmosphere. Humidity, temperature, wind speed, many other such weather variables globally. And that work has since then been published in Science, in the system called GraphCast. A more recent version has been published called as GenCast. And the work has also been integrated within traditional weather forecasting methods called, so there is this organization called the European Center for Medium Range Weather Forecasting, which is modeling the climate and the atmosphere and providing results of our simulations to other weather agencies around the world. So a few such organizations. There's also NOAA in the US, for instance. And so now ECMWF has started integrating as part of their offerings the forecasts made by AI models that are trained on climate data. Those models can be fairly useful. For instance, they have been demonstrated to work relatively well on the forecasting of trajectories of hurricanes. And you can read popular science articles about this, so it was mentioned in the New York Times with regards to the more latest hurricanes that happened. So the entire team has been working actively on manipulating those huge amounts of climate data, which are essentially at the scale of a petabyte.
Wow.
So a petabyte is basically 1,000 times a terabyte. A terabyte is something that can still fit in a laptop, a hard drive. That's no longer the case for a petabyte.
This was one very bored Sunday morning. I calculated how much paper you would have to print to take up, and trying to understand what a petabyte was in a material way. And I worked out if you printed 100 petabytes on A4 paper, double-sided, 10-point font, normal paper, piled it all up, you would have a pile of paper big enough to get from the Earth to the moon.
Okay.
So
yes.
The most random way I could figure out to demonstrate it, but that's, to give people an idea, that's how big a petabyte is of data.
Yes, no, that's a very great analogy. Well, I mean, how do we get to that number? So imagine that you are measuring the several variables quantifying the atmosphere, and you're measuring them on a grid of 30 kilometer by 30 kilometer cells, but that cover the entire Earth. So you have this grid of 1440 pixels, let's say, around the equator, and then 720 pixels from the North Pole to the South Pole. Well, then there is, of course, a discussion about projections. There's a whole discussion that can be done about this. So, but let's say that those data are stored in so-called equirectangular projection, which is like one cell per quarter degree of longitude and one cell per quarter degree of latitude. So that's why you get those numbers. Now you have that every hour for 50 years or even 100 years sometimes in the case of climate data, because we are predicting, simulating what happens in the future. Now you have this also at different altitudes. You can't just have a single cell at a geographical latitude, longitude. You actually need to model what happens at close to the surface, at sea level, and also what happens in the upper parts of the atmosphere. Typically, this can be up 47 levels. In the data set we've been looking at, we were looking at 13 levels in the atmosphere or 25 levels in the atmosphere. And then you need to also model temperature, the speed of wind, the so-called meridional and zonal wind. So that means basically along east-west or north-south.
Okay.
You can also model vertical wind. Okay, that's already 4 variables. And there's humidity. And there's this thing called geopotential, which is just a weird way of looking at pressure. I remember when I was a child, I was trying to understand weather forecast and why they were talking about isobars and showing those maps that essentially looked like altitude maps, but for pressure.
Yeah, the contour maps, yeah.
Contour maps for pressure. Yeah, so essentially, weather, the way the weather is modeled is not by vertical elevation, but by levels at the same pressure. And those levels, of course, oscillate vertically. So geopotential is related to the height or at that given pressure.
Measure the topography of the land, because I'm thinking, if you're in a flat plateau, the land won't have a massive effect. But if you're in a mountainous area, wind behaves strangely.
Yes, very good indeed. So actually, that's a great point here, because that is normally not changing. Topography is, you just need one of those maps and hopefully it lasts for a few years. But everything else is changing all the time. So the way those data are stored is every hour.
Right. So effectively for each of these cells, you're saying there's multiple variables. And there's obviously the topographical effects, which Christian said, which is static. But the variables, they keep on changing. So there's like a time multiplication to the data storage aspect. There is a altitude multiplication to the data storage aspect, because you're doing it at different altitudes. And then there's the size of Earth. There's a huge number of cells all around the world. So yeah, so I think we can get a intuitive grasp on why the data is so huge. And it keeps on growing, right? Because there's a time dependence, right? The longer you see, the more it gets.
Yes, and there is an additional dependence, which is the case for both climate and weather modeling, which is on the number of realizations. So let me get to that. You remember the curves produced in the IPCC report, the Intergovernmental Panel on Climate Change. You don't see a single curve of temperature up to 2010, forecasting the rise of temperature. What you see is a whole collection of curves, which show different outcomes from different models provided by the various organizations who are member of the IPCC. And then for each of those organizations, they don't run one model. They run that model 20 times, perhaps. And then they look at the outcomes and they compute statistics on the outcomes. The traditional weather models may be so-called deterministic, in the sense that if you run the same state of the atmosphere from them twice, you will get the same results. The way that agencies obtain different outcomes is by doing small perturbations of the atmospheric conditions at the beginning, and then propagating that through time and getting different outcomes. It's essentially an illustration of that butterfly effect.
And this is what the paper mentions as trajectories, right?
Yes, yeah, the trajectories of the atmosphere starting from some initial conditions of the atmosphere and then evolving over time following essentially the deterministic equations that govern fluid mechanics.
So in a brass tacks sense, what I'm hearing is climate science is a very exclusive science because what you're describing is an incredibly expensive research area, just in terms of data storage, but also compute to run models on vast amounts of data and to run multiple iterations of those models is so you've got both the compute and the storage cost. I'm not sure. I mean, you probably know. How small is that community? How many? Just in a ballpark figure, but are there like 5 agencies doing this kind of stuff, or are there hundreds, thousands? How much is that cost restricting the community?
Well, I think that every country has weather agencies that are working on those problems. They do, however, simulation results. So that's why I mentioned that the European Centre for Medium Range Weather Forecasting was essentially partnering with many countries across the world, providing the results of the simulations. And I know that they are dealing with modeling at the planet scale, but individual country may actually model the atmosphere at a fine resolution and maybe a shorter time horizon. So actually, the way we got into weather forecasting was through a slightly smaller problem, working with Met Office. I mentioned we were forecasting at the resolution of 1 kilometer and every 5 minutes. So you typically don't model that at the scale of a planet over 2 weeks, because that just would be prohibitively expensive in terms of resolving the equations and storing the data. But you can run a model localized, let's say, over the UK and UK islands over a few days in order to predict where exactly the rain clouds are moving and where exactly and when exactly it's going to rain.
You said all these countries have the agencies. So why don't they just solve it for their own country and not the whole world? There must be a reason why, if you solve it across the whole world, is your models better because they are not considering outside the cell influences?
Yes, exactly. I mean, you need to integrate the effects, the global effects, at a relatively short time horizon.
Just to give viewers an idea of the cost levels, the paper says storage cost in the cloud, obviously, because we cannot store 100 petabytes in our local drives, not yet, is around $1 million per month, $1 million a month.
Yeah, so this was a ballpark calculation that we did, looking at a few cloud providers, thinking about how much it would cost to store that amount of data. So the data set that we worked on ourselves, so it's called ERA 5. It's a data set of weather data that starts in time 1959 and goes until now. And it's a result of simulation and reanalysis. So what does reanalysis mean? You have to imagine that weather simulation is predicting the weather variables on this very dense grid, latitude and longitude, and also different levels of elevation at every time point, let's say every hour. But of course, we don't have sensors on this planet everywhere. We don't have weather stations everywhere. We don't have atmospheric balloons, weather balloons floating in the sky on a nice grid. So what happens instead is that these data are coming from simulation, but they are constantly being compared and adjusted based on the actual observations on the ground in weather stations and weather balloons in the atmosphere and satellite. So there is this, so the data in itself is in a way already like an interpolation done thanks to the simulation and the actual satellite and weather station observations. So there is a bit of error, of course, that has been introduced, but at the same time we have data that cover the entire planet very neatly. And that dataset in itself was, I think, a half a petabyte. But if you work, there's another dataset we've been working since, which is not yet mentioned in this published paper, which is called CMIP, Coupled Models Intercomparison Project. It's it's essentially the project behind the IPCC, Intergovernmental Panel on Climate Change reports, where multiple weather agencies are doing simulations at multiple universities are doing those simulations and then have multiple outcomes. And so this is where actually the storage blows up. Because you don't have just a single recording of the weather, but you have all those possible simulations. So that's how we get beyond several petabytes. And yeah, and just looking at the numbers of how much it would cost to store that on cloud, this is how you could get.
Right, right. And I think that this is what I was mentioning to as an enabler, right? Because this cost puts this problem out of reach of even trying for even big companies, right? Medium to big companies, right? It's only people who have that budget can even go in and store the data and then try to solve the problem, right? Storage of the data is pretty basic, I think.
Yes. Yeah, and data are being typically discarded. So they may be measured and something may be done out of them, but then because of prohibitive storage costs, they end up being discarded. And I think some satellite data are even in a worse situation.
Right. Okay, so I think we've kind of touched on the problem space, We've gone through the problem space, which is great. So, there is vast amounts of data, interesting, multi-dimensional data, multiple versions of data that the data science community need to work. So any team who wants to work on this needs, frankly, insane amounts of data. So this the paper is all about compression. So kind of get us into that. And how did you tackle that problem of just trying to reduce the petabytes?
So, in fact, as a stepping stone to that, can we talk about like your paper describes like lossy compression and lossless compression? So maybe let's start with that.
Yes.
Yeah, just for me, really, if no one else.
Well, so basically, lossy compression is, let's say, JPEG. You're losing parts of the information, but you're making the assumption that what you're losing is not crucial. Lossless compression is trying to actually store everything just with a smaller storage. So lossless compressions, we have lots of examples of this, is when you zip a file, you can get a reduction of size of perhaps a factor of 3 or a factor of 10, depending on how the original data, what actually the original data consists in. If your file is a text file and you just inadvertently press the spacebar for several hours, what you're saving at the end is effectively just spacebar multiplied by the number of time points, the number of seconds of which you've been holding the spacebar before sending the file. And I think that's the same for the fax machine. That's how it worked. That fax was not sending black-white pixels, but actually just black and then how many of those were coming.
All right.
So you get a good reduction, but what you need to begin with is data that is already kind of discretized. What I mean by that is it's already consisting of symbols. So letters, numbers, bytes. And so then you basically store indexes of those letters and how many times they occur. And there is also this thing called Huffman coding, and this goes into principles of information theory. If you can store something, you can store a dictionary of words in a more efficient way by the way you index those words. So you start with the most frequent ones and you give them a low number, so you don't need lots of numbers to describe them, and you're going to use them often. And if you have a very rare word, you put it at the bottom of a list, and you need a longer number to describe it, but it happens less often. So that's how you effectively manage to efficiently store that dictionary. Okay, so that's lossless compression. Can it really work with weather data? First of all, we have continuously valued data, temperature, maybe wind speed. Now the question is, what level of precision do we need when storing that data? But still, these are fundamentally continuously valued. There have been some studies done where you could reduce the resolution of the data that you store and get a compression ratio factor of 50 or X perhaps. But you would do it once you start discretizing the data. So imagine that if we had a picture You could store a picture with very rich color resolution, or you could decide to make it an 8-bit picture, an 8-bit image with only 8 levels of red, green, and blue. And so then it already starts looking like the graphics from a 1990s video game, but it takes less space. And then the other way of doing is like we have with JPEG. So JPEG is this strange compression format that is optimized for visual perception. And effectively, what JPEG does is it stores the low frequency content, but it starts to be much less precise on high frequency content. So if you compress a digital photo, you probably won't see a difference, even if you zoom in. But if you compress a black and white text document, you will start seeing those very noisy, dirty edges.
The artifacts around the edges.
Which are due to which was basically compression artifacts. So what we did, we basically trained our own JPEG system. But that was specifically targeted for weather data. And that was exploiting the visual properties, so to speak, of climate data. But we were also checking that, I mean, how much worse did the compressed result get? And what we were losing. And so we explored different amounts of compression. So it's called the rate distortion curve. You have different compression rates and you distort more and more as you compress more. And so when we look at that rate distortion curve, what is the maximum amount of compression you can tolerate before you start getting bad artifacts? So I have actually a picture to illustrate it because we've been I'm using a lot of my hands, but maybe I can show something. So let me try to share my screen some way. Yeah. So I have this window here, which is an extract from our paper. And this, so neural compression of atmospheric states, that's the paper that we published a few months ago in July, that we put on arXiv. And this is an example of the results that we get. So you have the original temperature and you have the reconstructed temperature. So they seem to kind of look alike. They are in the same range. This is temperature in Kelvin. So I guess 270.
Yeah, it would be a very hot day if that was centigrade.
Yeah, indeed. So 272, is it 0 degrees Celsius? I think. But then it's 1 degree Kelvin for 1 degree Celsius. Okay, so yeah, you can definitely recognize these trends look familiar, right? The Sahara Desert is pretty warm, relatively. And so now the interesting image is this one. This is the difference. And that is the result of a compression when we compress by a factor of 1,000.
1,000?
1,000 times smaller.
Wow, that makes my zip files feel pathetic all of a sudden.
Yes, but your zip files are not losing information. That would be really bad.
Yeah, but I think that that really makes the point about why Lossy is worth it.
Yeah, I mean, so you get 1,000 times compression, but let's just critically look, and I won't be offended if you say that what we do is problematic in a way. We have a whole paper trying to evaluate how much we lose and how bad it is. But here we're focusing on all those areas. We're highlighting the areas with larger errors. So the kind of statistics we are looking at from how much we're losing were the mean absolute error. So here we get like half a degree, okay? And the maximum absolute error, which is at the worst, we can be 5-6 degrees off in that specific case. And I'm going to slide down a little bit. So going at humidity, now looking at wind. So again, in our image of wind speed for the U component of wind, so wind along the east-west axis, this is how it looks like in the ground truth and reconstruction, and now the difference between ground truth and reconstruction. In that specific time frame, which was during Hurricane Matthew, I think, so in 5 October 2016. These were results we're getting. Yeah, we had some errors here off the US East Coast. And let's zoom a little bit. at the hurricane itself. So we have the ground truth, the reconstruction after compression. And so you see that there is a bit of blurring that happens. So just like in a JPEG, and looking at the extreme cases. Well, in the eye of a storm, that's where the error is the highest. And finally, and this is an important variable, it's called geopotential. So geopotential is related to pressure, but it's expressed in altitude. It's the altitude of the isobar surface as opposed to pressure itself. And so again, the Hurricane Matthew, is that. And we are comparing our method versus a baseline. So we were happy in that case that the baseline was not really showing the hurricane anymore, whereas we were still showing it to some extent, albeit with some errors. And so we're measuring the mean absolute error and the maximum absolute error. So I think a way of looking at the results of our paper, the sort of problem we are addressing makes the results consistently underwhelming, because everything we predict is wrong, right? Because we are compressing data in a lossy way. So it's worse than the original. So now the question only is, how much worse do you tolerate with respect to your storage needs?
Yeah, I suppose just to kind of rephrase that in a different analogy. Now, you've got, if I stand next to you, you have the real me. Mm-hmm. But if I send you a photo of me, it's not the real me. It is lossy. It's not as good, but you still recognize it absolutely.
Exactly.
If I get a 1-year-old child to draw a picture of me and I give you that, you probably won't recognize me. So, there is somewhere between in that scale, there's a threshold where it loses usefulness. And I think that's kind of what we're talking about, isn't it? So hopefully your 1000, compression, while yes, it isn't true perfect, is still usable enough that it works. Tell us, how did you examine that?
Yes, so there are different ways of looking at this. What we are looking at were extreme events. We wanted to check how much worse the extreme event forecasting was, and if we still had the important information stored. And so, for instance, we looked at, so I mentioned hurricanes, where we still were able to store information about the location of a hurricane, which was important.
Is it true that other attempts at this had successfully compressed the data but had lost kind of exceptional events? They'd kind of the data kind of smoothed them out.
So we're looking at examples of a heat wave that occurred in May 2015, which was called the 2015 Indian heat wave, and so we were focusing on the Indian subcontinent, and the question here was how much were we able to effectively model the extremes properly. And so looking at this specific image over there, we see that in general the error in the heat wave, which was a complete extreme event, were here in the blues, so under 1 degree Kelvin, with some small areas that perhaps would go to with an error of 2 or 3 degrees. So we managed still to maintain the important information about a weather event that had huge economic and health consequences with lots of deaths.
So are these images over time? Because I see, you've got them ranked there.
Yeah, exactly. Yes, so as the heat wave is progressing and moving over multiple time steps, indeed. Yes.
So anyone listening on the audio podcast, what we're seeing here is a map of the Indian subcontinent with color gradient to indicate temperature. So it starts with nearly all of the Indian subcontinent very, very, very red. And then next to it, we've got the model's version of that, which to the eye is, you would have said it was exactly the same image, but then the third image is the one that actually kind of properly compares that and maps out the differences pixel by pixel. And genuinely, you're seeing, at the extreme point when the temperature is at the highest, you're seeing hardly any differences. But even at the edge points where the weather systems are interacting, you've got cold weather over the Himalaya and very hot weather over the Indian Massif. You're still seeing quite marginal points of error there.
Yeah, exactly. There is another way of evaluation which would be to simply feed the results of our compressed presentations into a weather prediction model and see how this performs. But an alternative outcome for measuring the utility of our compression is to actually store in a compressed way, not necessarily the original trajectory, but the additional trajectories which are generated by a climate model. What I mean by that is when a climate model is running, there are multiple realizations, multiple trajectories, but multiple predictions that are made. And so one thing we can suggest is to store, of course, one reference point perfectly, but the 19 other forecasts to store them in a compressed way. And then you can still get the statistics of how much change and variability there is, thanks to your compressed presentation.
Just about following you there. So your paper is called Neural Compression. We've talked about Lossy and Lossless. What's the neural part?
We're actually getting at the heart of what deep learning and neural networks really are. These are compression techniques.
So when you talked about it being like, I think you said you were kind of doing a JPEG compression, that's kind of what you mean.
Right. So JPEG compression, that was an analogy.
Right. Yeah. That's useful for me. It's about as far as I can get.
Thank you. Well, so JPEG is not a neural network. It's just several researchers who coded up the way of storing spatial information in an optimal way and then discarding high frequency information in an optimal way. But what we did instead is that we trained an image generator. So at this point, maybe I should show how the system actually works. So effectively, if you think of all those algorithms, models that have been deployed in the past few years for image generation, such as, let's say, so Google released image generators called ImageN, and then you probably heard about DALL-E and Stable Diffusion. So these are all neural network-based models that at some point rely on convolutional neural network architecture to analyze fine-grained detail in an image, and then they represent information in a way that is stage-wise reduced in size. So they compress through a sort of bottleneck what information comes in, and then they generate something new. And you could actually just ask it to generate again the output from that bottleneck. So in our case, we take information coming around the globe, the weather data, so let's say temperature, pressure, wind speed, and we cut it into small squares. We cut the globe into 12 squares, so we have 12 square images, slightly distorted, and we feed those images through an autoencoder, so a neural network that is trained to predict its own inputs, but where the image goes through this bottleneck with much reduced capacity.
Right. So if I try to explain that, and please keep me honest, right? But Christian, yes. It's like the neural net is trying to compress it. So this is a bottleneck. It's saying, I'm not giving you whatever it is, like petabytes of storage, right? I'm giving you a small portion of that to store it in. And then on the other side, you have to reconstruct the whole model out of that small storage. So it's like iteratively trying to figure out the best way to represent and compress it so it can still reconstruct at the other end the actual image that is fed.
Actually, before I forget, there's a question I was thinking about in the shower this morning about this point. So if I've compressed my data, can I use the compressed data, or can I only analyze it when it's reconstructed?
You should be able to use it if you get the whole reconstruction.
Because your current models need that reconstructed data, right? That bottleneck, that representation is in sort of model specific. It's learned. Yes. The reconstruction is what we know. The reconstruction will be a temperature scale, where the learned bit will be a number which does not have any physical.
Yeah, that's what I was just thinking. If I could compress a petabyte down to 10 terabytes, it would obviously be great if I could work on the 10 terabyte data set and not have to whack it back up to a petabyte. Because
Right.
what I'm trying to avoid is even having to worry about ever touching petabyte scale data. So that's my question about when I reduce it down, can I use that compressed data in its compressed form, or do I have to reconstruct it back up to a petabyte?
Yeah, very good question. So in our current research, we only looked at the second part, which is to reconstruct and see how bad it is after reconstruction. But there is actually a lot to be done. This may be ongoing work and also work that could be picked on by others to take the compressed presentation, which is no longer pixels in an image, but simply these highly compressed symbols. So basically numbers between, let's say, 0, 8, and 8192. But instead of having 256 pixels by 256 pixels, you only have 32 by 32 of those numbers. So much smaller spatial extent. And yes, you could basically use it as input to a predictor to predict something else or to classify something else. So we are, in a way, learning a representation of input data. I'm sorry, interrupted you.
No. I was interrupting, but I was thinking like you could, and it's a give and take, right? But you could take the decoder piece, right? The piece that was converting that compressed back to the full scale representation, and you could put it in front of the current model. But it's a give and take, because here you don't have to store then the full representation, but now you have to compute every time you use it. You need to sort of blow that up before you compute.
Yes, indeed. So if you want to operate at the original scale, you need to decompress. So essentially, the autoencoder architecture that you've been using consists of this encoder that takes the original input and makes a code out of it, encodes it into a small presentation. And then there is this decoder that takes the compressed presentation and blows it up to the original scale. And that sort of autoencoder architecture is very frequent in many of the AI models that have been recently released, including in language models and image models. And it's because of every single one of those AI models is effectively compressing the data, that it finds interesting relationships between data points and interesting associations. There is a series of papers from about 10 years ago when language models were still in their infancy that were looking at the so-called distributional semantics. So the meaning of a word depending on the context in which the word happens and in which context those words happen. And so what those language models were doing at the time, they were representing long sequences of documents by small vectors of a few numbers. And each word also was associated with a vector of a few numbers. And then you could measure the distance between two words by measuring the distance between those two vectors, and measure distances between two documents by measuring also distances between vectors representing those documents. And you would all get that because, in a way, you were kind of compressing data, original text, into a small set of numbers and then making a prediction or decompressing. So it's just another way of phrasing that what we're doing in this compression algorithm is effectively the essence of deep learning. We are learning a small size presentation because we are constraining it to be small by design. But in order to do so, the model needs to learn some spatial correlations that happen in the data, some temporal correlations that happen in the data.
So it's kind of I get that. That makes sense. I see on screen you've got heel picks. I remember reading in the paper that the actual projection and the fact that the world is a sphere was a challenge in itself. Would you briefly touch on that, because I think that's a fascinating problem, and one I didn't expect there to actually be somehow.
Yeah. The problem with representing a sphere on paper is that you need to essentially make a choice of how you project that sphere. And typical projections have been relying on keeping all the lines of equal longitude parallel. And so you end up with the North Pole being essentially this very strange thing at the top of your image, or the bottom if you live in New Zealand, perhaps.
Gigantic Greenland.
Yes, gigantic Greenland, exactly. So it completely distorts all sense of perspective. And at the same time, this presentation can be useful if you look at a small scale. So the reason why Google Maps on a phone or Bing Maps or whatever that you may have on your smartphone is storing information maps in this Mercator projection. It's like storing longitudes and latitudes, but it's elongating. As you go further north, it's elongating the spaces between two latitude bars. So the reason why they do this is because if you zoom in into even a city very close to, let's say, the north of Norway, the streets still are normally aligned as they intersect at 90 degrees, which is important. But you get distortion if you zoom out, right? So it's like having a camera touching a sphere on the tangential plane or being very far from it and seeing the distortion. So here we considered various ways of projecting the sphere onto paper, and the one we went with is HuePix. So HuePix, what it does is that it cuts the sphere into 12 diamonds, which have this very cool property that every pixel inside that diamond, if you put it as a square, has the same area. So, for instance, there are four diamonds from HuePix that touch each other at the North Pole, and the corresponding pixel that is right at the North Pole on each of those diamonds has the same area as the pixel that is close to the equator on the diagonal opposite of that diamond.
Okay, which was definitely not the case for Mercator projections.
Exactly. So that the pixel over there has the same area as a pixel over there at the equator.
Got it.
I'm showing here on the mouse on the screen. And we thought that this would be important for essentially preserving some of the atmospheric properties, and the HuePix presentation is actually used by the climate community for the models. So that means that we simplify the problem from having to deal with a sphere into having to deal with 12 squares, 12 HuePix squares or diamonds.
And do you get challenges on the interfaces between these pixels?
Yes, they do happen. It's a very silly problem, but you need to make sure that the stitches or the seams are not visible. So we looked into this problem, and the simplest way was simply to actually work on slightly larger versions. And so let me go to the end of this 40-something page paper where I actually show how we are dealing with this. We created a new presentation of HuePix that has additional borders that go slightly beyond. And then we were training presentations on this augmented HuePix. And what that meant is that at reconstruction, we had overlapping pixels. And so we would do a proper interpolation between the two.
Clever. Got it.
Yes, and then the other aspect of working with this spherical data is working with so-called spherical harmonics, which it's a representation of data on a sphere that is equivalent to the Fourier transform on two-dimensional images. So it means we represent the spatial, the frequential content, but it is taking into account the fact that data are on a sphere.
This is mathematical slightly, right? This is something that one of my colleagues was mentioning, right? And he has done like a PhD in physics, and he was going through deep learning stuff, right? And he was saying, oh, the maths is not that difficult. And I'm like, yeah, it's not that difficult. And I've not had a maths degree, so I could still grasp it. But he was saying that in electrical, the field that I went in, and he's like, that was pretty difficult in maths because that has something similar here where we solve what is called Maxwell's equation in spherical dimensions. And the same equations using like the equations that we solve it are the Legendre polynomials. So that's a few polynomials that need to solve it in spherical dimensions cannot be used to solve it in cylindrical, which is another type of thing. So you need Bessel function to solve it, right? So it is very mathematical, but it certainly feels like the coordinate systems, they cannot easily translate. And the common way to think about it is if I ask you to draw a circle on a plain sheet of paper, you'd use a compass or something like that, right? But you're actually going around in a circle. But if I constrain you and say, no, you can only move like up and sideways, right? Up, down, or sideways. Can you draw a circle? You can never draw a circle, right? It will always be like a pixelated version of a circle. So between the coordinate systems, they do not translate. One quick question that I had was like, and I don't know if HealPix does this out of the box, but the Earth is not really a sphere.
Yes.
Did you find any issues with that being, Earth being a geoid?
No, we didn't.
Okay.
We definitely didn't look into. We just conveniently ignored this. I think it would be what that would effectively mean.
It would mean that your HealPix diamonds near the equator would be a bit more compressed, slightly more compressed than a sphere.
Then in order to, so I guess potentially what could be possible would be during interpolation itself. Projection from sphere to HealPix, maybe do some sort of distortion during projection.
Yeah, and learn that distortion because it's not uniform as well, right?
Yes, but then the problem occurs again in reprojection.
Correct, on the other side.
To go from HealPix images to latitude and longitude, we can very easily use the spherical harmonics, and we also use those spherical harmonics to compute the power spectrum of the image, essentially the frequential content at different scales. The lowest scale is basically variations that happen at planetary level, and fine scale is very local. High frequency, small scale, it's very local variations. But it will be difficult to actually adapt the spherical harmonics to non-spherical projections.
It's all of this maths is scaring me. I'm going to try and move us on a bit. It's way out of my ballpark. What I'm curious about is, so you've built the model. You said it was fine-tuned on weather data, and lots of things here which are specific to weather and the spherical globe, etc., etc. But the fact you've managed to get a compression model that is definitely viable and is getting 1,000 times compression. Weather data is not the only big data set in the world, so that this is a problem that exists in other domains. Curious about is I'm assuming that we couldn't chuck in, I don't know, traffic data and expect it to work because it hasn't been trained for that. But if I was to take the same technique, your neural compression thing, and kind of follow your path through the forest and use the same left turns and right turns, I should be able to take a different data set and get a similar result, I assume. If I'm right with that, what are the defining characteristics of a data set which would be a good candidate for this kind of technique?
I would say that the presence of spatial correlations is very important. So compressing just white noise would be extremely difficult, as opposed to compressing data that have spatial dependencies simply because they originate from a physical system where the atmospheric variables change.
So there has to be signal in the data.
Yes, there has to be signal in the data, and the weather variables change relatively continuously and smoothly, with some exceptions. At the coast or the mountains, during some extreme events, the change is much more fine scale. But this would be the first prerequisite. Our method has been working with still images, so we didn't even properly exploit temporal dependencies. But that is also something that could be exploited in learning to compress, and that's actually what video compression does in films. Potentially also the fact that the various variables have some sort of relationship. So we are not only compressing a single variable like temperature, but we are compressing at the same time temperature, wind speed, humidity. So these are all variables that come from the same physical system, our Earth atmosphere. And so there are also some relationships and correlations here as well.
Which is very interesting. Professor LeCun has this JEPA paper that he has published as well, which sort of goes into this, the temporal correlationships within the latent space, the compressed space as well. So that's quite interesting. Cool. I think we're done with the main part. We will go into the lightning round now. So, yeah. Christian?
I love the lightning round. Okay, right. So these are just kind of shoot from the hip kind of questions. So they're fun questions. So the first one, can transformers get us to AGI?
I don't think so, because this is just a single architecture for looking at processing data, but it doesn't tell us anything about where that data comes from, whether it is supervised learning or reinforcement learning. We may even run out of data you can think of.
Should we keep training larger foundation LLMs?
It's a very loaded question because it may come with what does the word should mean? Does it involve ethical questions as well regarding the data ownership and amount of energy that's used? I think there is, since the underlying data hasn't changed that much, I wonder what would be possible if we actually try to combine existing models or if you try to refine one model rather than just training from scratch each time.
Interesting.
Okay, good answer.
Who would you recommend people listen to? And who's exciting you at the moment? Maybe right question.
Wow, can I change medium?
Sure.
In the sense that instead of talking about podcasts, I can talk about performing arts instead.
For sure. Yeah.
Podcast. It can be like AI, data science podcast, whoever you are following. Right?
Yeah.
People in that space.
Yes. I don't quite know. I would simply, if it's really an off the hip answer,
shoot from the hip.
Say any live performance that deals with society and theater as an example. Yes.
Okay. Fair enough. This one's again a loaded question, as you'd say. What is the percentage chance of an AI apocalypse?
The question is loaded because it brings us with our own responsibilities.
Yes, it does.
So we really have a key to that answer. I would say that cooperation, regulation, and simply dialogue between people who develop the systems and people who use them is key to make sure that the outcomes are positive. So I'm actually relatively hopeful, even if sometimes you look at the news, it doesn't always seem so, but I am hopeful that on the average, we are going towards a better understanding of technology and of how it can be deployed.
I'm going to put a percentage
tending to zero somewhere.
Because I'm hopeful, I would place it at a few percent. Because I think we can still band together and make sure that we don't let AI-generated disinformation take over, for instance.
We've had interesting answers on this question. Anything from a hard zero up to, I think 40% was the highest so far.
Yeah, 30-40%. So yeah.
Yeah, and just to be clear, for me, an AI apocalypse doesn't involve a Hollywood scenario at all. It's simply mass disinformation, for instance. AI-generated slop inundating communication channels.
I think in some degrees that's already happened.
Yeah.
But maybe not apocalyptically.
Yeah.
Yes.
Okay, last question. This is a proper nerdy question. So favorite model, technique, language, what is the, you said earlier that, when I asked you about kind of, what you've observed over the years, that, the tools and techniques are so much more advanced now. So, what's the model technique or language that you really enjoy using?
Oh, gosh. Can I actually say MATLAB?
You can, yeah.
I really liked it at the time.
Do you really?
Okay. I have a fond memory of this because these were the times of my PhD, and I just loved stepping through the algorithm and being able to visualize what's going on exactly. So anything that actually allows you to probe and interrogate and demystify the black box you're working on. That would be so it doesn't have to be MATLAB, but essentially programming an IDE that allows you to really debug, an IDE and a set of libraries that allow you to really understand what's going on in the model, to trace the time it takes to execute each of the functions, to access the content of memory and plot the tensors. This would be my favorite.
Super. Thank you for that. Piotr, you have been an amazing guest and really, really, really lovely to have you on the podcast today. Thank you so much.
Yeah,
Thank you
thanks
for welcoming me and for a very fun conversation. It was really fun.
Thanks for listening, and join us next time on the IIAI podcast.